Next we discuss hydrolysis of salt. The interaction of anion or cation of the salt with water to produce acidic or basic solution is known as hydrolysis. The equilibrium constant of hydrolysis reaction is called hydrolysis constant. Let us consider a salt Mx, a salt of acid Hx and a base MOH. So Mx, when we add water we get Hx, acid Hx and base MOH. The general hydrolysis equilibria and hydrolysis constants are given by. So now hydrolysis of anion, if we consider, so Mx, when we dissolve in water we get Hx plus MOH, or if we consider only X minus here, so when we dissolve X minus in water we get Hx plus OH minus. So if we consider the hydrolysis constant Kh here of X, so we get X minus, we get Hx, so products Hx times concentration of OH minus by concentration of X minus. Now if we consider the hydrolysis of cation here, so cation is M plus, so when we add M plus, then if we add 2 H2 we get MOH plus H3O plus concentration. So Kh or hydrolysis constant of cation M plus is MOH, concentration of MOH times concentration of H3O plus by concentration of M plus. The fraction of the total salt that gets hydrolyzed at equilibrium is called degree of hydrolysis and is written as H. Now first we consider hydrolysis of salts of weak acid and strong base. The hydrolysis of the salts of weak acids and strong bases give alkaline solution. Okay, like if we consider as sodium acetate, on hydrolysis it gives acetic acid which is a weak acid and NaOH which is a strong base. That's why it said that the hydrolysis of the salt of weak acids and strong bases give alkaline solution. See, NaOH is a strong acid, so we get the solution is alkaline due to the presence of free OH minus. The example of these types of salts are CH3CONA or sodium acetate as we just discussed, and Na2CO3. Na2CO3 when we add in water we get NaOH and H2CO3, a carbonic acid. So NaOH is a strong base and H2CO3 is a weak acid, so we get alkaline solution here. Consider a general solution of a salt Mx by a strong acid MOH and a weak acid Hx. Since salt is a strong electrolyte, it is completely ionized into M plus and X minus ions according to the equation like this. So Mx, when we put in water, so we get M plus and X minus. Since Mx is a salt, so it will ionize like this. Since M plus is a cation of strong base, okay, it remains as such in solution, but the anion X minus reacts with water to form unionized Hx, which is represented by this. So X minus when adding with water gives Hx, which is a weak acid. That's why it says unionized, and OH minus. The hydrolysis constant is given by, so if you consider this reaction, the hydrolysis constant will be concentration of Hx times concentration of OH minus and divided by concentration of X minus, right. So for weak acid Hx, so Hx will dissociate like H plus plus X minus to some extent. So we get the value of Ka. So Ka of weak acid Hx is concentration of H times concentration of X minus, concentration of H plus times concentration of X minus by concentration of Hx. Also Kw, we already discussed, Kw is concentration of H plus times concentration of OH minus. So multiplying the numerator and denominator of right hand side of equation 1 by concentration of H plus, so this is the equation 1 here. So if we multiply concentration of H plus, okay, of equation y 1 by H plus, we get this expression. So we are multiplying equation 1 with concentration of H plus and we are dividing by concentration of H plus. So if we do it, we get like this, and now concentration of H plus times concentration of OH minus, that gives Kw, right. So this quantity gives Kw, and this quantity divided by Hx gives Ka, right. So Kh we get Kw by Ka. It is clear that the hydrolysis constant Kh of the salt is inversely proportional to the dissociation constant Ka of the weak acid. Therefore, the weaker the acid, the greater is the hydrolysis constant of the salt, right? Because we know for the weak acid Ka value is small. So, the weaker the acid, so since Ka is the denominator at 25 degree Celsius or 298 K, value of Kw we know. So, this kind of constant here. So since Kh is inversely proportional to Ka because it is in the denominator. So, lower the value of Ka, higher will be the value of Kh. So, lower the value of Ka means weaker the acid. So, that is why the Ka of the weak acid, for the Ka of weak acid, the hydrolysis constant of the salt will be high. Okay. Next, we discuss degree of hydrolysis. Let the original concentration of the salt in the solution be C moles per liter and H is the degree of hydrolysis at that concentration. So, X minus plus H2O, this is the reaction, so gives HX plus concentration plus OH minus hydroxyl ion. So, initial concentration is C, that is why we considered here, concentration of salt is C, and initially we do not have any HX or OH minus, so this is 0 and 0. So, at equilibrium we C times 1 minus H, because H is the degree of hydrolysis. So, C times 1 minus H, we get CH here, we get CH here. So, the hydrolysis constant Kh is products by reactants. So, concentration of Hx times concentration of OH minus by concentration of X minus. So, if we substitute this all this here, we get numerator, we get Ch times Ch, Ch times Ch by C times 1 minus H, we get this value. The quadratic equation can be solved by usual method, but it is simplified if H is small. If H is very, very small, then we can write 1 minus H as 1, right. So, if 1 minus H is 1, then Kh is C times H raised to the 2, or from there we can calculate H, or hydrolysis constant is root over Kh by C. Now, what is the value of Kh? We just discussed the value of Kh is Kw by Ka. So, if we substitute that here, we actually calculate the value of degree of hydrolysis, or H is Kw by Ka times C. So, this is the hydrolysis degree of hydrolysis. Then we discuss pH of the hydrolyzed salt solution. So, concentration of OH minus here, if we see concentration of OH minus is C times H. So, CH, and concentration of H plus then Kw by concentration of OH minus, right. So, Kw by CH. Now, substituting the value of H from equation 5. So, in equation 5 we have this one. So, H is root over Kw by Ka times C. So, if we substitute that here in this expression, so we get concentration of H plus is Kw by C and then root over Ka, this is the value of H. So, Ka times C by Kw. So, basically we get, this is the expression for concentration of H plus. So, what is pH? Now, if we take the log of concentration of H plus and if we put a minus sign, we get pH. So, pH is minus log concentration of H plus. So, minus log Kw times Ka by C raised to the half. Now, you take log in front of this, so you get minus half, then log Kw plus log Ka minus log C. Now, minus log Kw is nothing but pKw. So, if we substitute everything here, and then we get half pKw. So, this is half pKw, and minus log Ka is pKa. So, we get half pKa here plus half log C. Okay. So, at 298 K pH is pKw is 14, right, we already discussed. So, the equation 6 becomes pH equals to 7 plus half time 14 gives 7 plus half pKw times plus log C. Thus, knowing the molar concentration C of the solution, Ka and Kw, the pH of the solution can easily be calculated, right. So, Ka value if we know of a particular acid, so we can calculate pK. If we know the molar concentration of that acid C, and we know at 298 K we get value 7 here, and if we put all those values here, we can actually calculate pH of the solution. Next, we discuss hydrolysis of salts of strong acid and weak base. The hydrolysis of the salts of weak bases and strong acid give acidic solution. Before we consider the hydrolysis of salts of weak acid and strong base, so when hydrolysis takes place of a salt of weak acid and strong base, we get alkaline solution. But here, since the acid is strong, so we get acidic solution due to the presence of free H plus ion. The example of these types of salts are NH4Cl, CuSO4, AlCl3, etc. Consider a general solution of a salt MX from by weak acid MOH and a strong acid HX. So HX is the strong acid and base is weak base is MOH. Since salt is a strong electrolyte, it is completely ionized into M plus and X plus ion that we already discussed according to the equation. Mx plus H2O gives M plus plus X minus. Since X minus ion is a strong acid, it remains as such in the solution. But the cation M plus reacts with water to form unionized base MOH, which is represented by this. So M plus now is a cation. It reacts with H2O, gives MOH and H plus ion. The hydrolysis constant. So if we consider now hydrolysis constant, it will be Kh will be concentration of MOH times concentration of H plus by concentration of M plus. Now for weak base MOH, so MOH is the weak base we got here. So MOH will dissociate like M plus plus OH minus. So we can actually calculate Kb like we did before for weak acid K. We used Ka there. So here we used Kb. So Kb is concentration of M plus times concentration of OH minus by concentration of MOH. Also Kw we know, concentration of H plus times concentration of OH minus, we already discussed. Now multiplying the numerator and denominator of the right hand side of equation 7 by OH minus. So for the previous case we multiplied numerator and denominator by concentration of H plus, but here since here we have the OH minus, so we will multiply this word with OH minus. So here we get MOH, concentration Kh is your MOH. You see the value of Kh is MOH times concentration of H plus by concentration of M plus. So MOH times concentration of H plus by concentration of M plus. Now we have H plus here, that's why we are multiplying OH minus here, because our goal is to use this value of Kw, expression of Kw. So we are multiplying numerator and denominator both by OH minus. So we get MOH times concentration of H plus times concentration of OH minus by concentration of M plus by concentration of OH minus. Now this concentration of H plus times concentration of OH minus gives Kw, and concentration of M plus times concentration of OH minus by concentration of MOH gives Kb. So we get Kh equals to Kw by Kb. It is clear that the hydrolysis constant Kh of the salt is inversely proportional to the dissociation constant Kb of the base, like before. So Kh is inversely proportional to Kb, because Kw at 298 K, we know the value, it is constant. Therefore, so at particular temperature Kw is constant, right? Therefore, the weaker the base, the greater is the hydrolysis constant of the salt, because weaker the base, value of Kb will be smaller. So it is in the denominator, so value of the hydrolysis constant Kh will be higher of the salt. Degree of hydrolysis. Let the original concentration of the salt in the solution be C moles per liter, like before. We are following the similar, we will do the similar treatment here also. C moles per liter, and H is the degree of hydrolysis at that concentration. So M plus H2O gives MOH plus H plus. So initially we have C moles per liter. So concentration of M plus is initially C, and concentration of MOH 0 and concentration of H plus is 0. So at equilibrium we have H is the degree of hydrolysis. So C times 1 minus H, and MOH is CH, and H plus also, concentration of H plus is also CH. So here H is degree of hydrolysis. H is degree of hydrolysis. So the hydrolysis constant, like before, if we calculate, so hydrolysis constant Kh is concentration of MOH times concentration of H plus by concentration of M plus. Now we substitute the concentration of MOH by CH and concentration of H plus by CH and concentration of M plus by C times 1 minus H, we arrive at this expression. So Kh is CH raised to the 2 by 1 minus H. Since H is very, very small as compared to 1, so we can assume 1 minus H equals to 1 like before. So we get Kh is C times H to the H raised to the 2, and from there we can calculate the degree of hydrolysis H. So H is square root of Kh by C. Now if we substitute the value of Kh, we get H is root over Kw by Kb times C. Next we discuss pH of the hydrolyzed salt solution. So concentration of H plus is CH. So you see concentration of H plus is CH here. We need to calculate pH of the hydrolyzed salt. Okay, so concentration of H plus is C. What is the value of H? We just discussed the value of H is square root Kw by Kb times C. So if we substitute the value of H here, we get this is the term here. So we get concentration of H plus is square root Kw times C by Kb. Now if we take log, minus of log both sides, so we get the pH, because pH is minus log concentration of H plus, so we get pH is minus log Kw plus Kw times C by Kb raised to the half, and then we take half in front of this log sign, we get minus half log Kw minus half log C plus half log Kb. Now minus log Kw, we know pKw, and minus log Kb gives pKb. So we get pH is half pKw, this is half pKw, minus half pKb here, and this is minus half pKb here, and we get minus half log C. Now at 298 K, pKw is 14, so the equation becomes pH is, now it is 14, so half times 14 again like before, so we get half times 14 means 7 plus half pKb plus half log C, right. So this will be your minus sign here, not plus. Thus knowing the molar concentration of the C of the solution, Ka and Kw, the pH of the solution can be calculated like before. Next we discuss hydrolysis of salts of weak acid and weak base. In this case, both the cation and anion undergo hydrolysis to the same or different extents. The resulting solution may be neutral, acidic or basic depending upon the relative strength of acids and base. Since here both weak, we are considering both weak acid salts of weak acids and weak base, so we need to consider relative strength of how weak the acid is or how strong the base is. So according to that, the resulting solution may be neutral, acidic or basic. Some common examples are ammonium acetate, ammonium carbonate, and aluminum phosphate, etc. Let us consider a salt Mx formed by the weak acid Hx and weak base MOH. The salt in aqueous solution is completely dissociated into ions. Like before, we do the similar treatment here. So Mx plus H2O gives M plus X minus. Since both the cation and anion are of weak base and weak acid respectively, both of these hydrolyze in water. So M plus X minus plus H2O gives Hx plus MOH. So the hydrolysis constant is given by concentration of H plus, Kh is concentration of MOH, concentration of Hx by concentration of M plus by concentration of X minus. Now for weak acid, Hx dissociates like this. So we get the value of Ka, expression of K, dissociation constant K is concentration of H plus times concentration of X minus by concentration of Hx. For weak base, again base is also weak, so MOH will dissociate like this, M plus OH minus. So we get Kb is concentration of M plus times concentration of OH minus by concentration of MOH. And we also know value expression for Kw. Kw is concentration of H plus times concentration of OH minus. So multiplying the numerator and denominator of the right hand side, of equation 13. So this is equation 13. Now you see in the equation 13 we have MOH, HX, M plus and X minus. So by H plus, concentration of H plus and OH minus both, right? So we get, so if we multiply numerator and denominator both by concentration of H plus and times concentration of OH minus, so we now rearrange this one, MOH, concentration of MOH by concentration of M plus times concentration of OH minus, and HX here we have, so HX by concentration of X minus times concentration of H plus, right? So we are now rearranging everything, times concentration of H plus times concentration of OH minus. So what do we get? So this quantity will give us 1 by kW, 1 by kb, this will give you 1 by kb, this will give us 1 by Ka, and this will give us kW, right? So we get Kh is kW by Ka times kb. Next we discuss degree of hydrolysis. Let the original concentration of the salt in the solution be C moles per liter like before, and H is the degree of hydrolysis at that concentration. So initially, so the corresponding equilibrium is M plus X minus plus H2O gives HX plus MOH. So initial concentration of salt is C, so M plus is C, X minus is C, this is 0, this is excess we are using, HX is 0 and MOH is 0. So at equilibrium, because we have used C moles per liter, we multiply C in 1 minus H, because H is the degree of hydrolysis, and concentration of X minus is also C times 1 minus H, HX is CH and MOH CH. Now if we calculate hydrolysis constant Kh is product, concentration of products by concentration of reactants, so CH times CH by C times 1 minus H times C times 1 minus H. So we get C, both the C's will get cancel each other, so we get this thing H2A constant A square by 1 minus A square. The quadratic equation can be solved by usual method, but it is simplified if H is small. So if H is very small, we can consider that if H is small, so compared to 1, so denominator is 1, so we get Kh is H square, or H is root over Kh. So if we substitute the value of Kh here, so we get H, value of H is root over square root of Kw by Ka times Kb.